Welcome everyone to
Workshop number 8.
Workshop 8, that's the one. Today we're going to be looking a bit more at how to actually build working diagrams, build from working diagrams in OpenRocket and have that as a CAD file that's actually ready to 3D print.
In Onshape.
In Onshape, yes, I'm gonna mix those names up a lot. So I'll start off actually by just showing people what you can really do with Onshape. Some of the sort of cooler features, how complex you can actually get, how high level you can make things. So if you...
I'll stop sharing screen. Yep. Go ahead.
So this is a personal project of mine. It's a planetary gear assembly, where if you spin this input, you can actually see that. So I've modeled the parts in Onshape, just sort of basic, you can see some chamfers on the edge there. You can see some cutaway extrudes, all stuff you would have come across if you went to last week's workshop. So, all this sort of stuff, and then you can actually assemble it all together. And, so you say that, okay, this thing spins around that thing, this thing has that gear relation to the other. And you can start getting stuff like... Slides to work. Come on. Well, it's got stage fright, but it still does it if you do it manually. So you can see I can actually drag around parts physically the way I want. And because of all the dependencies I've set up, it actually interacts. It behaves in a physically realistic manner. And it lets you actually, design things very easily and see what they'll actually be doing in real life. So Onshape is pretty cool. Now, does anyone by any chance have a OpenRocket CAD file, OpenRocket file that they would like me to model and turn into a 3D printable CAD file? Doesn't need to actually be a fully flyable thing, as long as it, looks roughly like a rocket. It'll be good to show people how to model a rocket. See someone in chat. All right, I might steal Hassan's then. Here is one I prepared earlier. So this is, similar to the design we went over in earlier workshops. Just nose cone, cardboard tube, 3D printed fins. In fact, I have one sitting here that I've actually flown before. I'll stop sharing for a second just so it zooms in on my screen. Yeah, Hassan, I don't know if the recording picks up everyone with their video on, so it's probably easier to just let me have my video on. And then that's just going to be the thing that shows up in the YouTube video, all right?
Yeah, it's usually the active speaker, so pretty much sure it's going to be you.
Okay. Oh, apparently anyone with their video on shows up. So anyway, excuse the mess, but this is a flight tested version of our rocket designs. So you can see here, 3D printed nose cone, slots into cardboard tube, same connection for the 3D printed fin can. The motor is held inside there. And before flight, this is actually taped up so it doesn't come off. This is the nose cone that pops off. Parachute comes out, and shock cord down through that to the motor mount. So basically,
it's the same one that we're looking for in the campsite, right? Not the campsite, like the bush hole.
Yeah, that was the one we lost in the long grass and had to spend a little while walking around to find. But that was part of the fun. So this is very similar design, little bit skinnier, a little bit shorter, but we just dimension that and we will be able to do it. So I will actually, can I share multiple screens at once?
Bring them in the same window, maybe.
I mean, if I just share my entire screen, I guess. And I control to select multiple windows. There we are. Okay. So are you seeing me switch between these, or are you seeing both at once?
Yeah, we can see both.
At once?
Like when you're switching. No, not
okay,
one.
so you can see me switch between them. Cool.
Yeah.
Anyway, so basically I'm going to take this, use this as an engineering drawing, which is basically what it is. It's a 2D, drawing of a design, and I need to then take this drawing, take its measurements, and put it into CAD. This is a very, similar thing to what you'd encounter in industry. You'd be working off drawings and getting it ready for manufacture. I will talk a bit as well about how to actually design something for manufacture, in this case 3D printing, because you can't just have any old geometry. You have to have something that can actually be physically made by the method that you are using. So we'll start off with the body tube, just to give ourselves our dimensions. This is going to be cardboard, so we're not actually going to be 3D printing it, but it's always good to include reference parts in, CAD models that you're making. So you can see here, okay, 180 mil long, 24.8 on the outside with a 2 mil wall thickness. And the way I'm going to do this is I'm going to create a sketch. I'm going to have a vertical line like that. Actually, easier would be to actually make a rectangle because it is the three-dimensional part. And I can see the box that's highlighted there. This is how Onshape works. You just start writing numbers, and if that box is highlighted after you've just created a shape, you start inputting dimensions. So it was 180 mil long and 2 mil thick. And then I'm going to set a dimension from here to here. So this will tell me the outer diameter, and I can actually drag this across, I believe, to make, no, that's only with lines. That's fine though, because, so 24.8 outer diameter, and then you can just actually do maths in your dimensions, which is very nice for people like me who cannot do mental maths. So we now have the beginnings, and I'll should be able to symmetric line or linear edge. Cool. So I'm going to make a construction line as well, just to help me make things symmetrical. I select this, and then I select that and that, and that just centers it nicely around the midpoint, makes things neat. All right. Construction line has just the central axis of my rocket. And I'm going to revolve that face around this axis. And There you go, tube. So again, like basic stuff, but you know, stuff that you need to be able to do. Now I will create. I'll start work on the nose cone. So we can see the nose cone is a half of an ellipse, and it is. I'll just make these numbers a little bit nicer. It's 85 mil long, 24.8 mil in diameter. And we'll just have it as a 2 mil wall thickness. When we talk about the wall thicknesses of 3D printed parts, we need to keep in mind that we want them to be a multiple of 0.4 millimeters, because the nozzle of a 3D printer is 0.4 millimeters. And so when it's laying down beads of, 3D printed plastic, you want those to be sitting right next to each other and neatly make up the thickness of your wall. So in this case, 5 times 0.4, 2 millimeters. So we're going to have 5 wall thicknesses and have a nice strong part. So, I select the plane for my second sketch. And I'm going to actually hide this for a moment because it's easier when working in 2D to just compare it to dimensioned part. So another construction line just because I can vertically.
I believe this is the diameter of the outside of the tube, like including the outside.
Correct.
Yeah.
Correct. So what I'll do is I'll reference to that, and that will be all good. I'll insert an ellipse with a vertical edge. That's that. So I can see here that it's showing me the major axis is highlighted, ready for me to put a value in. I check my open rocket. I see it's 85 mil that I want. 85 mil, there we are. And then yes, 24.8. Oh, well, I already constrained that, so that's fine. I'm going to turn this into a construction line because I don't want it actually modeled. And I'm going to just extend it out. Nope. I'll add a construction line here as well. And that is so that I can use the trim tool to take off the lower half of that nose cone and this half as well, because we're going to do a full 360-degree revolve. Now, here, cool. So here I'm going to do something a little bit. It's telling me it's coincident. Okay, so here we're seeing I believe, an artifact of the tessellation quality of this part. So basically, it's, instead of drawing an ellipse, it's approximating an ellipse. So while it's telling me that these lines are coincident, it's not actually showing up on the model. Part of the fun of 3D CAD modeling, though. Let me see if I can. Any Onshape pros know how to force better tessellation on parts? Ah, never mind. I'll survive. Oh, hang on, we're getting some chat. Anyway, onwards. We have that model. Okay, this is really annoying me actually. So I'm going to leave that for now. I'm just going to have it sideways. So, sorry about that little hiccup, but back to it. So with a 3D printed part that has to fit into another dimensioned part, what you want is similar to, as you can see my camera, similar to what I have here. You want a bit of a angle on your part so that even if the sizing is slightly off, it will just slide, the first part of it will slide nice and neatly into your, cardboard tube or whatever you're trying to fit it into. And it'll just fit nicely together. So that's what we're going to do here. And you only need about a half of a degree of an angle, or about, half a millimeter of difference. Appearance, edit tessellation quality. Now let's check if that is possible for sketches at all. Yeah, for parts. Okay. Well, when we get to the parts, I'll do that. Thank you for chasing that up, though, Cass. Excuse me. So, what I'm going to do now is I'm going to edit the sketch and add some more dimensions. So I know that I want the difference here to be 0.5 millimeters approximately. And for the length of this insert, yeah, generally 10 to 15 is a good amount. I'll just chuck it at 10. And now thinking back to what I was saying about you want a consistent multiple of 0.4 for your 3D printer when you're talking about thicknesses of your parts. So for example here, if I were to draw something like this with a vertical inside, and so if this was my part, I'll just do hang on. So if this was the cross section of my part here, you can imagine that maybe if I had, so maybe down the bottom, I'll dimension this to, I'll make it 1.2. We'll work with roughly thinner walls. So 1.2, that's a multiple of 0.4. So we'll have nice 3 beads of plastic nicely laid down by our 3D printer, and that'll be fine. But as we make our way up, you can see because the thickness is varying, you'll start to get gaps in your 3D print, which weakens the structure. So you don't want this having one side tapered and one side not tapered. And the way we are going to make sure that that does not happen is we're going to use the offset tool. And that is a really good way of just making sure that even for curves, you have nicely, so I can see there, box pops up, you have nicely consistently 1.2 apart shapes, basically. Now, it is a little bit different for curved parts, but that's sort of another rabbit hole that we won't go into in this workshop. Anywho, so I'm going to make this, and that, so yeah, I'm going to try one last time to sort of make this work. Okay, now that I've done that, that's working. So I should probably click on them instead of using the shortcuts. beg your pardon. But so what I've done is just trimmed off all the lines, and then that's neatened things up and made things actually coincident and lining up. Again, I'm pretty sure this was just a visual sort of bug, but something you have to consider. So now, dimensioning, I'll make sure that I used the wrong tool there. So I'll make sure that here it's 1.2 across, as well as at the top being 1.2 across. And so that means that even on this crossways sort of this angled bit on the horizontal section, it's still, so even, what is this? Okay, different degrees apart, that's okay then. Okay, 1.2, 1.2, drive it down to there. Okay, another of the joys of 3D printing, over-constrained of 3D CAD, over-constrained sketches. Anyway, we've gotten there now. We can see here we have our lovely nose cone. One thing again you don't want with 3D printing is an overhang, because you can imagine if it's trying to stack layers on top of each other, once it gets up to here, there's no support for it to start stacking plastic on top of. So you want it to just give it a nice gradual sort of line. Trim this part out, add a line here. And then we can see if our, so using the, sorry, I don't need the extrude function, I need the revolve function. So that can be spun around this axis, and yeah, I'll go over that again in a second, Kenny. So thank you very much for the question, but there is also a picture that I'll show you that actually demonstrates what can go wrong when you don't do the layering correctly. So I'll bring that up in a second. Thank you for bringing that up though. Thank you very much. So you can see here, this is what our nose cone will look like. You can see that, yeah, again, no overhangs. I will show you now what a problem with an overhang can actually look like. So we have, so this is from, I assume everyone's seeing my Google Chrome screen here.
Yep.
Yep, cool. So this is actually the uni's 3D printing page where you can actually submit your prints. We'll get people access to this very soon. We do have access to it. Basically, the only thing you need to do is when you're submitting a print, make sure you follow these guidelines that they have in these documents. So, it has to be in the right format. You have to use the right program to turn your STL into a printable file. And STL is basically, one of these that's saved as sort of a triangular mesh. Anyway, so they have this wonderful document which goes into things you have to keep in mind when you're designing a 3D printed part. So here you see the problems that you can get with a large overhang. So I'll zoom in a bit. So you can see a little bit here, the layer lines, where the 3D printer has come along and done a new layer of plastic. So it would have made this entire base layer, one layer on top of the other, and then started making up these little funky shapes. So it's done a layer here, then another one, etc. When it gets to this little part that's hanging over and it's suspended in free space, you can see there's a little bit of a, I don't know, bit of gloop that's dripped down because the hot plastic that's getting deposited by the 3D printer has nothing to be put down on top of. You can see here and here and here, that problem gets a lot more pronounced when that overhang is made bigger. So yeah, basically you need a, support such as here. You can see that these ones on the right hand side, they've printed fine because they're steep enough that the overhang is not too great, and you can just stack each layer on top of the other and get a nice print. But again, as you get too steep, there's more material overhanging than there is supported in each new layer, and then you start to get issues with drooping, etc. Does that answer your question there, Kenny? It looks like we've lost Kenny. That's all right. Edwin understands. I'm very glad. So basically, yeah, that is why you need to make sure that when you're designing something for 3D printing, you can imagine building it up, bit by bit from the bottom and having it sort of stand up as its own structure. So yeah, so anyway, that's, I understand. I know I did go rushing through that a bit, but that is just like something you can refer back to. And when you need to make a nose cone, okay, put in these dimensions, make sure that the walls are a multiple of 0.4 of the nozzle distance away from each other. Make sure that you don't have any overhangs that are too steep so that you don't get, bad 3D prints like these examples. And that will get you a nice nose cone for your rocket. So we can see here, and again, so I had this angle here. This can be made a little bit smaller, but this angle here is again to prevent too steep an overhang. That can be played with a little bit. You can see it here on this rocket. It doesn't have to be too big. Hang on, the screen blur is blurring it out, isn't it? So yeah, you can see the little lip on here. It only has to be like 1 mil, half a mil. So it's not super noticeable, but it strengthens your 3D print and it still fits in nicely. So, okay, question in chat.
Looks like Kenny's back.
Good. Kenny's back. I'll just quickly mention this again. So yeah, Kenny, the reason you need an overhang is because everything has to stack up nicely on top of each other. Otherwise, you get problems like this where you don't have enough support material beneath your print and it starts drooping and failing. Cool. So that is what gets us our nice looking nose cone. We'll maybe select a color for that by editing its appearance. Make it white like my PLA is. We'll make our cardboard tube. We'll edit the appearance of that just so we can keep track of everything as well. That's close enough. Any other questions in chat? Excellent. Yeah, no worries, Kenny. All right, so now moving on to the fin can, a bit more of a complicated part. I'll show you more detail on the finished version. But so basically the things you need it to do is, of course, have fins so that your rocket is stable. It needs to fit into the cardboard tube nicely. You need to have a tie down point for your parachute line. You can see here I've sort of just made a hole in the structure that I can tie that off to. It needs to hold the motor. So the fins, all 4 of them, extend into the middle to hold the diameter of my motor. And it needs to stop the motor from getting pushed up too far into the rocket. So you can see that it's very blackened now because of the char from the launch, but that is a sort of I don't know what you'd call it, but it's a motor stop to stop the motor going further into the rocket, making sure that it's held nicely in place. So we'll do that now by creating a sketch. I will hide my cardboard tube for a moment so I can see the cutaway version a bit easier. I'll make a construction line down the middle to make things easy. And we'll start off with the easy bit, similar to what we did with the okay, so similar to what we did with the nose cone, the interfacing part. So I'm just dimensioning this. You want, again, about 0.5 mil difference there. You want these two to be roughly. So using the dimension tool here to give it 1.2, and then that will make sure those are nicely in line, etc. as well. So there's the interface part. We'll now be adding this out to go to the full diameter. And again, I can just be very sloppy with my initial line placement because I can just put dimensions in after the fact. Not that way though. Forgot to do that. Oh yeah. So now we add a vertical line down. And we want this to be approximately 70 mil long, because if we have a look in our Open Rocket document, we can see that if we go into motors and configuration, that lets us check the exact motor that we are using. We're using a C610. We can see that that is 70 millimeters long and 18 millimeters in diameter. We'll need that measurement as well. So we're designing this section just at the rear here, and we want the motor to be sticking out the back a little bit, roughly a centimeter, so that when we actually want to pull the motor out or put the motor in, we have clearance to our fingers, basically. So yeah, 70 mil long, and then the motor isn't going to be going all the way up here. We're going to have the motor block somewhere around here. So it's going to be 70 mil long, and then the motor is going to be sticking out the end of it. Anyway, so we will good stuff. See you, Kenny.
Yes. Oh, anyway. I think he already left.
Yeah, all good. Anyway, again, we make sure our walls are nice even multiples, etc., etc. That can get dragged to here, and we want, again, going to our dimensions tool. These two need to be 1.2 apart, and that all connects up nicely. Excellent. So this is going to be the outer shell of our lovely rocket. And so if I show that again, we can see how this is sort of starting to come together. So now we just need to add the fins and the internals to this lower section. Excuse me. So I'll create a new sketch I'll edit the same sketch to get the fins going. I'll hide these parts. That. I'll be editing the sketch. Excellent. Okay, so first of all, I'll add the motor block, which is what's going to stop the motor from being pushed up the inside of the rocket. So that just needs to be a nice solid. I'll just put that there for now. We'll trim it off later while we add our dimensions. So we want from where the motor is going to sit. Actually, first of all, I think I will, sorry, this is a little bit back and forth, but I'll actually add my motor dimensions into this as a separate sketch so that we have something to reference off. Just makes it things easier. I normally just have the measurements in my head, but it'll be better to be able to show them. So I'm making a sketch like this, and the motor is going to be 70 mil long, and it's going to be, what do we miss here? Not 1 divided by 2, 18 divided by 2. It's going to be 9 mil in diameter. And we can move that up and down. But we can see here that, we're going to roughly be sticking out here. We wanted it to be sticking out the end by approximately 10 mil, 1 centimeter. And so this is the space that our motor is going to be occupying. So we can have a look back in this sketch and see, roughly where things are going to be happening. Okay. The chronology of this is a little bit messed up, so I'm just going to add it into this sketch. Like that. Cool. Okay. Motor is in. Dimension it to be, that's pretty close, 1 centimeter away. Bring this to hold it. This can get pushed back because we only want to be holding the edge of the motor, so we don't need this constricting the flow of the ejection charge, because so we light the motor down here, the motor burns through, a bit of a fuse, and then a burst of black powder, the ejection charge, is what's going to go through this tube and push the parachute out the top. So we don't want to constrict that too much. We're just going to want to be holding on to the motor by its edge. So around about that is good. We will trim off all these extraneous pieces. Excellent. And so this will be the inside of our, so yeah, we can see there we have our motor stop. Doesn't have to be, follow a super precise formula, as long as it's just holding in the edge of the motor and stopping it from going further into the rocket. And of course, as long as it's supported on both sides, with that bit of an overhang, just add some bracing, it's all good. Now, it's time we add the fins. So we'll add another sketch. We will hide some of our parts to make it easier for us. And remember, we had the fins extending into the inside. Just see if I can line that up. So the fins were to extend into the inside to actually hold the motor. So we're going to run the line of the fins up to this motor. And I'm just going to draw the rough shape of the fins, and then we're going to dimension them. Excellent. Okay, so we know our fins are going to be roughly this shape, but then we go back to our open rocket design. we double click on the part to bring up the configuration. Okay, we have 4 fins. The root chord, which is this baseline here, is 50 millimeters. So I'm going to dimension from here to here. That's 50 mil. The height is 30 millimeters. So I'm going to dimension from here to here, 30. The tip chord is 20 millimeters. So that's the tip here, 20 mil. And the sweep length has sort of been done for us. The difference between 50 and 20 gives us, this 30 mil. Excellent. You can see that that's grayed out because that's a driven dimension, not a driving dimension. So these 2 dimensions just dictate what that will be. If I change this, it doesn't affect the sketch. So we have that, and we just double check that all matches up. That's beautiful. And then one last thing we want to do is we want to add a little bit of clearance in between where our motor is going to be and where the edge of this is going to be. Because if we make our 3D parts to exact tolerances, and 3D printers can be quite accurate, but if we run our dimensions right up to what we want them to be holding, then they are going to be too tight. You need to leave a little bit of a gap. Otherwise, you're going to be sanding down your parts, basically. So if we dimension here to here, no, it doesn't want to do that. Okay, I'll just hide that sketch real quick. Okay, if we dimension between here and here, it's giving us 3.4 millimeters currently. So I'm just going to knock 0.4 mil off that. That'll give me plenty of room. It's because I had a coincident constraint. So I'm just going to try and delete these coincident constraints. Excellent. I'm going to try and take this across like that. I do still want this to be coincident, not the other. So sometimes it does take a little bit of sleuthing around. Thanks, guys. But there we go. We'll, okay, so that is 3 mil, that's good. We'll make sure that this is set to vertical. There we are. And so we can see here we have a nice 0.4 mil gap between the side, and that's that's a sort of a rule of thumb, but that works quite well, having a 0.4 mil gap for most of your 3D printed parts when there's a tight fit. You can make up the difference with a little bit of masking tape in this case if it's too loose, but this is sort of roughly what you want your gaps to be. So we finish this sketch, we see we have a fin. So all we need to do is, well, we can just thicken this in both directions. And again, thinking of, we want to make these walls a multiple of 0.4. So we'll have reasonably thick fins going 0.8 mil in both directions. Give us a 1.6 millimeter thick fins. And those are going to be new parts, which I might just rename to fins. And now we can just set a circular pattern of these fins around this central axis. 4 fins. Excellent. I will just do one more thing actually. and that will be adding a little bit. So hang on, I'll just show you why I'm doing this. So you can see on the inside, if I get rid of all of that sketches, we actually got ourselves a decent looking rocket. It'll all fit together. The you know, nose cone fits into the cardboard tube, and the bottom section fits into the cardboard tube. We can see here, you know, we want to just not have the gap between this and this part. We want to run it all the way up, just give ourselves a bit more structural integrity, a bit more strength. So I'm just going to do that with the fins now. So I'm just going to add some lines vertically up there. This is all going to be joined into the same part anyway, so I don't have to be too precise. I'm going to trim away, trim away this little bit, and then that's all good. And I've made sure that everything is like more than overlap, so when I fusion them together, which is what you're going to see in a little bit, that there's no possibility of little tiny gaps on the inside of my design, which would lead to bad things in 3D printing. So if I bring everything back, you can see now on the inside, the fins run up nicely into this little support area here. And that's all good. I'll get rid of these sketches again. And now all we need to do is run a Boolean operation to join these parts all together. If you don't have parts that need to be connected, properly connected, you can start running into problems with your 3D printing software, trying to print them as separate parts, even though they're intersecting. So you do want to be using the Boolean tool to create a union of all these parts, turn multiple parts into one, and then yeah, you have a completed rocket. The overhang for the motor stopper. So you're talking about, are we going to get this problem of, you know, the prints failing possibly due to the overhang being too steep on our motor stopper? Is that roughly, is that sort of?
Yeah, I was just wondering.
So basically, so you can sort of see here that this 45-degree angle actually prints quite nicely, and about 45 degrees is actually the rule of thumb for how you want to be designing your parts in 3D printed. So you can do, you know, you can have a big section going up and then tilt sideways and keep printing, and that's going to be fine. It's just when you start getting too steep that you start to run into these problems. So yeah, use 45-degree as your rule of thumb for how steep you want your overhang to be.
Okay, awesome. Thanks, Ben.
No worries. Thank you for the question. And so yeah, this is a rocket that, you know, provided you have the right size cardboard tube, would be able to be printed off. Just these two parts could be printed off at the Uni 3D printer, and it could be ready to fly. You'd just super glue. Honestly, you're similar to what I have done on the inside of here. So I have super glue and just tape over it for when it was drying, but I've just super glued the inside of the parachute line to the inside of my nose cone. The same can be done for this lower fin can as well. And this is, yeah, a quite acceptable design. So that is how you design parts for 3D printing. Make sure that you have all your overhangs right. Make sure your wall thicknesses are a multiple of 0.4. Make sure all your parts are intersected, and yeah, you'd be good to go. So that brings us to roughly 50 minutes of runtime. Any questions now? No worries, Edwin. So the plan is to try and get some people I believe in-person workshop next week, if possible, is the plan.
Yep.
Excellent. So yeah, well, basically, we're going to be trying to get some people to be getting their open rocket designs printed out and start assembling them. Either assembling them or just troubleshooting rough designs in next week's workshop, which is planned to be in person. And yeah, so you can get a design like this printed out and yeah, assemble it next week with us and fly it at the Druin launch, which will be on the 15th of May. So yeah, good stuff.